और स्वागत है आप सभी का हमारे शिट पोस्टिंग चैनल पर। तो आज हम लेकर आए हैं आप सभी के लिए एक नई सीरीज। इसका नाम है RWM, रीड विथ मी। तो आप सभी सोच रहे होंगे कि मैं ये चैप्टर 7 क्यों पढ़ रहा हूँ अभी। तो मैं आपको बताना चाहता हूँ कि कल मैंने पहले से लेकर छठे चैप्टर को पढ़ा था, लेकिन कल मैं अपनी मूर्खता की पराकाष्ठा पर भी था। तो इसी वजह से 4 घंटे 4.5 घंटे तक पढ़ने के बाद मैंने देखा कि मैं रिकॉर्डिंग ऑन करने ही भूल गया था। उससे मुझे बहुत बड़ा धक्का लगा और मैंने छोड़ दिया कि चलो नहीं करेंगे इस सब। लेकिन आज मैं वापस आ चुका हूँ। इस किताब के 7वें चैप्टर को रीड करूंगा आज। असल में पहले मैं सोच रहा था कि मैं एक दिन में 10-10 चैप्टर पढ़ूंगा। तो मतलब मैं चाहता था कि मैं इन दोनों किताबों को, जो वॉल्यूम 1 और वॉल्यूम 2 है, इनको अपनी गर्मी की छुट्टियों के खत्म होने से पहले पढ़ डालूं पूरा। लेकिन कल का वीडियो रिकॉर्ड करने के बाद मुझे ये रियलाइजेशन हुआ कि मेरा जो गला है वो इतना नहीं झेल सकता है। तो अब मैंने ये डिसाइड किया है कि मैं एक दिन में एक ही चैप्टर पढ़ूंगा। और आप लोग ये बिल्कुल मत सोचना कि मैं आपके लिए पढ़ रहा हूँ, ठीक है? मैं अपने लिए पढ़ रहा हूँ और बस मेरा मन किया तो मैं रिकॉर्ड कर रहा हूँ। असल में मैं एक JEE करके एग्ज़ाम होता है, उसको उसकी तैयारी कर रहा हूँ, लेकिन नाम का एस्पायरेंट हूँ वैसे मैं। अ, पता नहीं क्या होगा मेरा। तो मैं सोच रहा था कि इसको डाल ही देता हूँ यूट्यूब पर रिकॉर्ड करके। काहे कि मैं अगर खुद से ऐसे ही पढ़ते रहता तो मैं पहला दूसरा चैप्टर ही 10 बार कर डालता, ठीक है? लेकिन अब मैं रिकॉर्ड कर रहा हूँ तो थोड़ा सा मतलब थोड़ा थोड़ा बंधन लग रहा है, ऑल्दो नहीं है बंधन। लेकिन फिर भी थोड़ा थोड़ा एहसास होता है, तो मतलब थोड़ी मदद मिलती है तो क्या दिक्कत है ये सब करने से। ठीक है, तो चलिए अब बहुत हुआ, इसको चालू करते हैं। ठीक है, तो चैप्टर का नाम है सर्कुलर मोशन, angular variables. Suppose a particle P is moving in a circle of radius r. Figure 7.1. Okay. Let O be the center of the circle. Let O be the origin and OX the x-axis. The position of the particle P at a given instant may be described by the angle theta between OP and OX. Hmm. Okay. We call theta the angular position of the particle. As the particle moves on the circle, its angular position theta changes. Suppose the particle goes to a nearby point P dash in time delta t, so that theta increases to theta plus delta t. Delta theta. The rate of change of angular position is called angular velocity. Thus, the angular velocity is uh, omega equals to d theta 1 dt. The rate of change of angular velocity is called angular acceleration. Thus, the angular acceleration is alpha equals to d omega by dt equals to, yes, double differentiation of theta with respect to t. If the angular acceleration alpha is constant, we have theta equals to omega naught t plus half alpha t square. Omega equals to omega naught plus alpha t. Omega square equals to omega naught square plus 2 alpha theta. Okay, where omega naught and omega are the angular velocities at t equals to 0 and at time t, and theta is the angular position at time t. The linear distance p dash traveled by the particle in time delta t is uh, delta s equals to r delta theta. Uh, Dividing both sides by delta t, we get v equals to r omega, where v is the linear speed of the particle. Differentiating equation 7.4 with respect to time, the rate of change of speed is a equals to r d omega upon dt. Uh, At equals to r alpha. Remember that a equals to dv by dt is the rate of change of speed and is not the rate of change of velocity. It is therefore not equal to the net acceleration. We shall show that a t is the component of acceleration along the tangent, and hence we have used the suffix t. It is called the tangential acceleration. एग्जाम्पल 7.1। मैं ये एग्जाम्पल्स को बिल्कुल भी रीड नहीं करने वाला हूँ आपके लिए, मैं बस देख लूंगा इसको अपने लिए, क्योंकि एक और बार आप लोगों को बता दूं कि मैं आपके लिए नहीं इसको पढ़ रहा हूँ, ठीक है, मैं अपने लिए पढ़ रहा हूँ। अच्छा, ये तो बहुत छोटी सी चीज है। अच्छा, हाँ, ये भी बहुत छोटी सी चीज है। Unit vectors along the radius and the tangent. Consider a particle moving in a circle. Suppose the particle is at a point P in the circle at a given instant. Figure 7.2. Take the center of the circle to be the origin. Align OX as the x-axis and a perpendicular radius OY as the y-axis. The angular position of the particle at this instant is theta. Okay. Draw unit vector PA vector equals to E vector R, ER vector along the outward radius, and a unit vector PB vector equals to ET vector along the tangent in the direction of increasing theta. We call ER vector the radial unit vector and ET vector the tangential unit vector. Draw Px dash parallel to the x-axis and Py dash parallel to the y-axis from the figure. Okay. Uh, from the figure, PA vector equals to I cap PA cos theta plus J cap PA sin theta, or ER vector equals to I cap cos theta plus J cap sin theta, where I cap and J cap are the unit vectors along the x and y axis respectively. Similarly, PB vector equals to this. Okay. Acceleration in circular motion. Consider the situation shown in figure 7.2. It is clear from the figure that the position vector of the particle at time t is r vector equals to op vector equals to op r vector. Oh, okay, equals to this. Differentiating equation. वेट इट इज नॉट अ वेक्टर। नहीं, मैं थोड़ा सा मूर्ख हूँ यार, तो उसके लिए कुछ नहीं किया जा सकता। डिफरेंशिएटिंग इक्वेशन वन विद रिस्पेक्ट टू, ये ई आर वेक्टर जो है ये यूनिट वेक्टर है। ओके, और मैं हाँ, तो मैं मूर्ख हूँ भाई, बहुत बड़ा मूर्ख। अब मैं समझ नहीं पा रहा हूँ कि इस दिमाग के साथ मेरा हुआ क्या। Differentiating equation 1 with respect to time, the velocity of the particle at time t is v vector equals to dr vector upon dt equals to this, okay, r vector। ये पूरे में आता है अपना ये r ओमेगा, और ये यूनिट वेक्टर है। हम्म। नहीं, वेट। हाँ, तो एक सेकेंड यार, अब मैं कुछ तो, खैर क्या कर सकते हैं, मेरी मूर्खता का कोई इलाज नहीं है। हाँ, वैसे ऐसा भी नहीं है कि मैं या आखिरी बार और पहली बार पढ़ रहा हूँ इस चैप्टर को, मतलब पहली बार तो पढ़ रहा हूँ, लेकिन आखिरी बार नहीं। मैंने इस किताब को इस वजह से उठाया है जिससे कि लेक्चर देखते टाइम मैं उसको 2x स्पीड तक पे देख सकूं, जिससे कि मुझे ऐसा लगे कि मैं ये सब चीज़ें पहले भी पढ़ चुका हूँ। ठीक है, अगर ऐसा करूँगा तब 2x पे मुझे समझ में आएगा, ऐसा मुझे लगता है। ठीक है, तो नहीं आया तो मैं उसमें कुछ नहीं कर सकता, भाड़ में जाए। The term r omega is the speed of the particle at time t. Equation 7.4. Uh, where is, अच्छा ठीक है, याद कर लिया है इसने। अरे यार, मैं पीछे क्यों गया था अभी। And the vector in the square bracket is the unit vector et cap along the tangent. Thus, the velocity of the particle at any instant is along the tangent to the circle, and its magnitude is v equals to r omega. The acceleration of the particle at time t is a vector equals to dv vector upon dt. From 2, we get this. ये इक्वेशंस पढ़ना मुझे दिमाग खराब मेरा करता है। मैं इसको डिक्टेट नहीं कर सकता, लेकिन समझ सकता हूँ एटलीस्ट। तो हाँ, समझ ही लिया है मैंने। ठीक है, where er cap and et cap are the unit vectors along the radial and tangential directions respectively, and v is the speed of the particle at time t. We have used this. Okay, okay. Uniform circular motion. If the particle moves in the circle with a uniform speed, we call it a uniform circular motion. In this case, dv by dt equals to 0, and equation 7.8 gives a vector equals to minus omega square r er cap. Uh, Thus, the acceleration of the particle is in the direction of minus er vector, that is towards the center. थोड़ा सा पानी पी लेता हूँ, मैं तब बताता हूँ। The magnitude of the acceleration is ar equals to omega square r equals to v square upon r. Thus, if a particle moves in a circle of radius r with a constant speed v, its acceleration is v square upon r. directed towards the center. This acceleration is called centripetal acceleration. Note that the speed remains constant. The direction continuously changes and hence the velocity changes. And there is an acceleration during the motion. Oh. Mm. अ, तो अब एग्जाम्पल को मैं अपने लिए रीड कर लेता हूँ आई भी नॉर्मली ये एचसीवी के जो एग्जाम्पल्स हैं ये थोड़े से नॉर्मल लगते हैं मुझे। मैंने बहुत ज्यादा तो पढ़ी नहीं है, मैं 2 दिन से ही पढ़ रहा हूँ इसको। क्योंकि काफी लोग बोल रहे थे कि बहुत इंपॉर्टेंट बुक है, बहुत इंपॉर्टेंट बुक है। और मैंने एक हार्ड कॉपी भी मंगवाई थी जिसको मैंने एक समय के बाद खोल के नहीं देखा। हालांकि मैंने पहला और दूसरा चैप्टर बहुत बार पढ़ा है, मतलब अ, उससे आगे मैं बढ़ ही नहीं पाता था कभी। इसीलिए तो मुझे जरूरत पड़ रही है वीडियोस बनाने की। अगर मैं ये ना कर रहा होता तो मैं अभी वापस से वही पहला दूसरा चैप्टर पढ़ रहा होता आज भी। मैं बहुत बार पढ़ा है उसको। ओके। Non-uniform circular motion. If the speed of the particle moving in a circle is not constant, the acceleration has both the radial and the tangential components. According to equation 7.8, the radial and the tangential accelerations are this and this. Thus, the component of the acceleration towards the center is omega square r equals to v square upon r, and the component along the tangent along the direction of motion is dv by dt. The magnitude of the acceleration is this. Yes, it is simple. Yeah. The direction of this resultant acceleration makes an angle alpha with the radius where tan alpha equals to dv by dt upon v square upon r. ओके, तो एक और एग्जांपल आ गया है। हाँ, ये भी सिंपल ही है, फॉर्मूला पे ही है सब। Dynamics of circular motion. If a particle moves in a circle as seen from an inertial frame, a resultant non-zero force must act on the particle. That is because a particle moving in a circle is accelerated and acceleration can be produced in an inertial frame only if a resultant force acts on it. If the speed of the particle remains constant, the acceleration of the particle is towards the center and its magnitude is v square upon r. Here v is the speed of the particle and r is the radius of the circle. The resultant force must act towards the center and its magnitude F must satisfy E equals to F upon m, or V square upon R equals to F upon m, or F equals to mv square by R. Okay, this is centripetal force. So yes, it should be clearly understood that centripetal force is another word for force towards the center. This force must originate from some external source, such as gravitation, tension, friction, Coulomb force, etc. Centripetal force is not a new kind of force, just as an upward force or a downward force is not a new kind of force. Okay. Oh, it is simple. Circular turnings and banking of roads, I guess। ये पढ़ा था हम लोगों ने शायद से एनएलएम में। मैं अभी 12वीं में हूँ ना असल में। ये और मैंने 11वीं में बकवास की है केवल। हाँ तो लेट्स कंटिन्यू। When vehicles go through turnings, they travel along a nearly circular arc. There must be some force which will produce the required acceleration. If the vehicle goes in a horizontal circular path, this resultant force is also horizontal. Consider the situation as shown in figure 7.4. A vehicle of mass m moving at a speed v is making a turn on the circular path of radius r. The external forces acting on the vehicle are weight mg, normal contact force n, and friction F static. If the road is horizontal, the normal force N is vertically upward. The only horizontal force that can act towards the center is the friction F static. This is static friction and is self adjustable. The tires get a tendency to skid outward, and the frictional force which opposes this skidding acts towards the center. Thus, for a safe turn, we must have v square upon r equals to f static upon m. F static equals to mv square by r. However, there is a limit to the magnitude of the frictional force. If mu static is the coefficient of static friction between the tires and the road, the magnitude of friction F static cannot exceed mu static n. For vertical equilibrium, n equals to mg, so that F static is lesser or equal to mu static mg. Thus, for a safe turn, mv square by r is lesser or equal to mu static mg. Okay, और this okay. हजार रूप बनाए जा सकते हैं ऐसे तो नहीं, हजार तो नहीं, लेकिन कुछ तो बनाए जा सकते हैं। और friction is not always reliable at circular turns if high speeds and sharp turns are involved. To avoid dependence on friction, the roads are banked at the turn so that the outer part of the road is somewhat lifted up as compared to the inner part. Figure 7.5. Yes. The surface of the road makes an angle theta with the horizontal throughout the turn. The normal force N makes an angle theta with the vertical. At the correct speed, the horizontal component of N is sufficient to produce the acceleration towards the center, and the self-adjustable frictional force keeps its value 0. Applying Newton's second law along the radius and the first law in the vertical direction, n sin theta equals to mv square by r and n cos theta equals to mv. These equations give tan theta equals to v square upon rg. The angle theta depends on the speed of the vehicle as well as on the radius of the turn. Routes are banked for the average expected speed of the vehicles. If the speed of a particular vehicle is a little less or a little more than the correct speed, the self-adjustable static friction operates between the tires and the road, and the vehicle does not skid or slip. If the speed is too different from that given by equation 7.13, even the maximum friction cannot prevent a skid or a slip. Example 7.6, let me read it. It is like formula based, I was. Yeah. Centrifugal force. We discussed in chapter 5 that Newton's laws of motion are not valid if one is working from a non-inertial frame. If the frame translates with respect to an inertial frame with an acceleration a naught vector, one must assume the existence of a pseudo force minus m a naught vector acting on a particle of mass m. Once this pseudo force is included, one can use Newton's laws in their usual form. What pseudo force is needed if the frame of reference rotates at a constant angular velocity omega with respect to an inertial frame? Okay. Suppose the observer is sitting in a closed cabin, okay, which is made to rotate about the vertical z-axis at a uniform angular velocity omega. Here is 7.6. The x and y axes are fixed in the cabin. Consider a heavy box of mass m kept on the floor at a distance r from the z-axis. Suppose the floor and the box are rough and the box does not slip on the floor as the cabin rotates. The box is at rest with respect to the cabin and hence is rotating with respect to the ground at an angular velocity omega. Let us first analyze the motion of the box from the ground frame. In this frame, which is inertial, the box is moving in a circle of radius r. It therefore has an acceleration v square upon r equals to omega square r towards the center. The resultant force on the box must be towards the center and its magnitude must be m omega square r. The forces on the box are weight mg, normal force n by the floor, friction F by the floor. Figure 7.6b, where is 7.6? Oh, okay, B shows the free body diagram for the box. Since the resultant is towards the center and its magnitude is m omega square r, we should have F equals to m omega square r. The floor exerts a force of static friction F equals to m omega square r towards the region. Now consider the same box when observed from the frame of the rotating cabin. The observer there finds that the box is at rest. If he or she applies Newton's laws, the resultant force on the box should be zero. The weight and the normal contact force balance each other, but the frictional force F equals to m omega square r acts on the box towards the origin to make the resultant zero. A pseudo force must be assumed which acts on the box away from the center, radially outward, and has a magnitude m omega square r. This pseudo force is called the centrifugal force. The analysis from the rotating frame is as follows. The forces on the box are these: D, centrifugal force, m omega square r. The free body diagram is shown in the figure 7.6c as the box is at rest. Newton's first law gives F equals to m omega square r. Note that we get the same equation for friction as we got from the ground frame, but we had to apply Newton's second law from the ground frame and Newton's first law from the rotating frame. Let us now summarize our discussion. Okay, how long is this? अच्छा 2 पेज बाकी हैं केवल. ठीक है. ये हिंदी बोलकर मैं काफी कंफर्टेबल महसूस करता हूँ। असल में मैंने पिछली जो वीडियो बनाई थी जिसमें मैंने 6 चैप्टर पढ़े थे, वो पूरी मैंने अंग्रेजी में बनाई थी। पता नहीं क्यों, लेकिन बनाई थी। अब हिंदी बोल रहा हूँ तो काफी कंफर्टेबल सा महसूस हो रहा है, और हिंदी ही बोलूंगा। मुझे इतना सीरियस मैं हूँ नहीं इस चैनल के प्रति, तो मेरे को कोई फर्क वगैरह पड़ता नहीं है किसी भी चीज से। और मैं क्यों बोलूँ भाई अंग्रेजी। अब छोड़ो इन सब बातों को और आगे चलते हैं अपने डिस्कशन में। अरे मतलब मैं रीड कर रहा था तो उसको मैं आगे बढ़ाता हूँ। ठीक है, सपोज वी आर वर्किंग फ्रॉम अ फ्रेम ऑफ रेफरेंस that is rotating at a constant angular velocity omega with respect to an inertial frame. If we analyze the dynamics of a particle of mass m kept at a distance r from the axis of rotation, we have to assume that a force m omega square r acts radially outward on the particle. Only then we can apply Newton's laws of motion in the rotating frame. This radially outward pseudo force is called the centrifugal force. In fact, centrifugal force is a sufficient pseudo force only if we are analyzing the particles at rest in a uniformly rotating frame. If we analyze the motion of a particle that moves in the rotating frame, we may have to assume other pseudo forces together with the centrifugal force. Such forces are called the Coriolis, uh, the Coriolis forces. The Coriolo, the Coriolis forces. Coriolis forces. Uh, the Coriolis force is perpendicular to the velocity of the particle and also perpendicular to the axis of rotation of the frame. Once again, we emphasize that all these pseudo forces, centrifugal or Coriolis, are needed only if the working frame is rotating. If we work from an inertial frame, there is no need to apply any pseudo force. It is a common misconception among the beginners that centrifugal force acts on a particle because the particle goes on a circle. Centrifugal force acts मैं नींद में हूँ मुझे लगता है, और इसको मैं खत्म होने के बाद तुरंत सोने जाऊंगा क्योंकि मैं कुछ भी प्रोनाउंस नहीं कर पा रहा हूँ। टाइम क्या हो रहा है एक बार चेक कर। तो अभी 3:50 हो रहे हैं रात के। रात की क्या, सुबह होने वाली है, भोर हो रही है। भोर हो रही है। ये effect of Earth's rotation on apparent weight. The Earth rotates about its axis at an angular speed of 1 revolution per 24 hours. The line joining the north and the south poles is the axis of rotation. Every point on the Earth moves in a circle. A point at equator moves in a circle of radius equal to the radius of the Earth, and the force of the circle is same as the center of the Earth. For any other point on the circle on the Earth, uh, the circle of rotation is smaller than this. Consider a place P on the Earth, figure 7.7. Okay. Drop a perpendicular PC from P to this axis SN. Okay, SN. Oh, south north. The place P rotates in a circle with the center at C. The radius of this circle is called CP. Okay. The angle between the axis SN and the radius OP through P is called the colatitude of this place P. We have CP equals to OP sine theta, or R equals to CP is R, eh? of this smaller circle, radius of CP is R of this smaller circle, and capital R is the radius of Earth. Capital small r equals to capital R sine theta, where capital R is the radius of the Earth. Okay. If we work from the frame of reference of the Earth, we shall have to assume that the existence of the pseudo forces. In particular, a centrifugal force m omega square r has to be assumed on any particle of mass m placed at p. Here, omega is the angular speed of the Earth. If we discuss the equilibrium of bodies at rest in the Earth's frame, no other pseudo force is needed. Consider a heavy particle of mass m suspended through a string from the ceiling of a laboratory at co-latitude theta. Figure 7.8. Okay. Looking from the Earth's frame, the particle is in equilibrium, and the forces on it are a gravitational attraction mg towards the center of the Earth, centrifugal force m omega square r towards Cp, and the tension on the string T along the string. Okay. As the particle is in equilibrium in the frame of Earth, the three forces on the particle should add up to zero. The resultant of mg and m omega square r equals to mg dash, where g dash equals to this. I'm not going to read equations. ठीक है, मैं ये सब नहीं करता यार, कि अभी मेरा वैसे ही सिर दर्द होता है. Also, the direction of this force of this resultant makes an angle alpha with the vertical OP. Okay, where tan alpha equals to omega square r sine theta cos theta upon g minus omega square r sine square theta. As the three forces acting on the particle must add up to zero, the force of tension must be equal and opposite to the resultant of the rest. Thus, the magnitude of the tension in the string must be mg dash, and the direction of the string should make an angle alpha with the true vertical. The direction of g dash is the apparent vertical direction because a plumb line stays in this direction only. The walls of the buildings are constructed by making them parallel to g dash and not to g. The water surface placed at rest is perpendicular to g dash. The magnitude of g dash is also different from g, as 2g is greater than omega square r. It is clear from equation 7.14. I did not read equations. एक बार okay, I have read it now. That g dash is greater than g. One way of measuring the weight of a body is to suspend it by a string and find the tension in the string. The tension itself is taken as a measure of the weight, as T equals to mg dash. The weight so observed is less than the true weight mg. This is known as the apparent weight. Similarly, if a person stands on the platform of a weighing machine, the platform exerts a normal force N, which is equal to mg dash. The reading of the machine responds to the force exerted on it, and hence the weight recorded is apparent weight mg dash. At equator, theta equals to 90 degree, and equation 7.14 gives this. ओके, और mg dash equals to mg minus m omega square r. This can be obtained in a more straightforward way. At the equator, m omega square r is directly opposite to mg, and the resultant is simply mg minus m omega square r. Also, this resultant is towards the center of the earth, so that at the equator the plumb line stands along the true vertical. At poles theta equals to 0, and equation 7.14 gives g dash equals to g, and equation 7.15 shows that alpha equals to 0. Thus, there is no apparent change in g at the poles. This is because the poles themselves do not rotate, and hence the effect of Earth's rotation is not felt there. Okay, तो अब एक एग्जाम्पल बाकी है बस। अ, इसको तो वैसे ही मैं खुद पढ़ूंगा, तो चलिए मैं इस वीडियो को रोक देता हूँ। अब की बार सेव कर लूंगा पक्का से।